Okay, we have 3 more examples left in these notes, and these last 3 examples are going to be where we are simplifying, basically simplifying as much as we can. So I'm going to preface this with, you can do these problems usually in more than one way. I'm going to show you the way that I think to do the problem first, but you might think of something different, and that is okay. We should just end up with the same result. All right, here we go. So I'm just going to look at this and say, thinking about algebra, what do I see that I could do? The first thing that I think of is I think of distributing, right? This is multiplication. I know I can distribute those things, so I'm going to do that. So that's going to give me secant squared minus secant of x plus secant of x minus 1, all on the top. Still have this sine squared on the bottom. Okay, keeping on that path of what can I do algebraically. Negative secant and positive secant, that would be 0, right? Because those are like terms. So I would end up with secant squared of x minus 1 over sine squared of x. Okay, now I have 2 options at this point. I could decompose this fraction like we did in the last video, or I could use a trig identity, a Pythagorean identity. So there is a Pythagorean identity, and you can flip back to your notes if you would like, but there's a Pythagorean identity that says 1 plus tangent squared is equal to secant squared. Now that's not exactly what I have going on right here, but I could rearrange it and probably make it look like this. Because what I need is I need the secant and the 1 to be on the same side. So let me think about how I could do that. I think I could just subtract the 1, right? So if I were to subtract the 1 in this Pythagorean identity, I get something that looks exactly like the numerator. And it says secant squared minus 1 is the same as tangent squared. So I'm going to make that substitution. So that top is just going to be rewritten as tangent squared over sine squared. We haven't really done anything with that denominator yet. Okay? And again, it's kind of hard to tell sometimes when you're supposed to stop and when you're supposed to keep going. I would say you just keep going until there's nothing left for you to do. So right here, might look like you can't do anything else, but you can do a little bit, because tangent squared, or not tangent squared specifically, but just tangent itself can be written as sine over cosine. In this case, they'd both be squared. And then what I can do, looks like I just made my life a lot harder, but I promise you it's going to fix itself here in a second. What I can do next is I can do something called outer inner. And I don't know if we've talked about that yet this year, but outer inner is a way of dividing a fraction by a fraction. Okay, so it's just a little trick. Outer inner means to take the 2 very outside things, so like very top and very bottom, multiply those together, which would make it sine squared, and then take the inner things and multiply those together and put that on the bottom, and that would be your solution. And then it looks like sine squared will cancel with a sine squared. So my final answer, option 1, could be to write it as 1 over cosine squared. But then remember, possibly remember that, oh yeah, 1 over cos is the same as secant. So this could be also written as secant squared. Okay, let's look at another one. This one, they're going to give us more distinguished directions. So what it says is to simplify, and they specifically request that we get a common denominator. Okay, so we're going to do that first. These 2 denominators don't have anything in common. So we're going to use the old trick where if they don't have anything in common, you just multiply by the opposite denominator. So I'm going to multiply this first fraction by cosine, because that's the denominator over here. And I'm going to multiply the second fraction by 1 minus sine, because that's the denominator over there. Basically, the name of the game is just be real careful. Okay, so first fraction is going to look like cosine squared x. And then on the bottom, I'm not going to actually distribute or anything. I'm just going to call it cosine x and then 1 minus sine x, like that. Okay, on this side, let's distribute the sine. So that would make it sine x minus sine squared x over the denominator. Okay, right now my thought process is just keep working on this common denominator deal. And so remember that when you get a common denominator that allows you to add the numerators together, or in this case, subtract them. Okay, also notice I put plus sine squared. That's because if you're subtracting a negative, it becomes a positive. All right. Still looks pretty messy. There's got to be more that we can do. Okay, in the directions it says get common denominators. Check, we did that. Use Pythagorean identity to simplify. So Pythagorean identities, remember, are these ones here in the boxes. Do any of those Pythagorean identities look like they might fit in this scenario? Okay, I want you to look right here. Do you see how the top has a cosine squared plus a sine squared? If you wanted, you could even rearrange and put them right beside each other. But the fact that there's a cosine squared plus a sine squared means that we can apply a Pythagorean identity. And the one that we're applying is the one that says that cosine squared plus sine squared is equal to 1. So I can take those two terms out and write it as 1 in their place. There is still a negative sine x that has to come along. Okay? Now watch how beautifully this ends up working out. 1 minus sine x cancels with 1 minus sine x. So you end up with 1 over cosine of x, which would be an okay answer, but we could do a little better by calling it secant of x. Okay. Last one. So find all values of x in the interval from 0 to 2 pi that solve this equation. All right. Obviously, this equation is a mess. So the first thing that we would want to do is we would want to try to rewrite it. So I'm going to start with, let's just keep cosine cubed over sine kind of the way it is. But let's write cotangent. That would be cosine over sine. So the way I've rewritten it, this allows me to actually cross multiply to simplify the expression. So I'm going to cross multiply. All right, and then I end up having a sign on both sides. So those two things would cancel each other out. And then what we can do is we can subtract. Actually, let me write this first. We can subtract the cos of x over and move that over to the other side with the other cosine, which is not a bad idea because they are both like terms, or not like terms, both cosines. So this is going to create sort of like a factoring situation. Keep in mind, this is kind of like if you had a to the third minus a equals 0. You could factor in a out of each term. Do you see where I'm going with this? So that's what I'm going to be doing here with the cosines. I'm going to factor a cosine out of each term. And I'm going to set, actually, you know what? I can factor this even further because this would be like a plus 1, a minus 1. So I better do that. Let's do that one more step. So I'm going to end up with cos of x, and then this would be cosine of x minus 1 times cosine of x plus 1. Okay, so we've got it factored all the way down. Now what we're going to do is set each of these products, each group, equal to 0. Like this. And we're going to solve each equation. Okay, so to solve each equation, now you have to dig into your brain and remember the unit circle. So for this first question, this is kind of like asking me what x value would make cosine equal 0, or just when is cosine 0 in the unit circle. That is in two places, pi by 2 and 3 pi by 2. Okay. Over here, I need to solve it a little bit further by adding the 1. So now I'm asking myself, when is the cosine equal to 1? Cosine is equal to 1 at 0 or 2 pi, whichever one you want to call it. And then I have one more step that's asking me when is cosine equal to -1? That is at pi. Notice all the answers I chose to write are in this interval, 0 to 2 pi. Okay, there's one final step with this question, and that final step is we have to check these answers to see if they actually work in the problem, okay? Because here's what could happen. You see how you have a denominator in this original question? Well, it's possible that one of these values, if I were to plug it in, I could get a 0 in the denominator, and that is not computable. So we could have an extraneous solution here, okay? So I'm going to just quickly plug in. I'm just going to focus on the denominator because I really just don't want that to be 0. And I also don't want cotangent to be undefined. So we got to kind of just focus here on this denominator. So let's start there. If I plug in pi by 2, sine of pi by 2 is equal to 1, which is not 0, so that one's fine. Good to go. 3 pi by 2, sine of that value is -1, so that one's fine. However, when you plug in 0, sine of 0 is 0, so this value is extraneous. 2 pi would also give you, sine of 2 pi would also be 0, so that's also extraneous. And then pi would do the same thing because sine of pi is also 0. So all of these values here are considered extraneous because when you plug them back into the original equation, they make the equation incomputable.